Hello everyone, welcome back to another episode of the problem solving series. In today's video we're going to be covering torque. I will preface here and say that I'm not going to cover static equilibrium in this video. I'm going to save that for a separate video. So if that's what you're looking for, that's either coming or hopefully is already out and is going to be somewhere else. Otherwise, we will get into talking about torque. So we've been going in this direction in the past couple of videos of these rotational analogs for these linear physical quantities. We covered rotational kinematics and moment of inertia, and now we're going to be talking about torque, which is the rotational analog for force. So when we talk about, or when we have talked about force in the past, we've been talking about forces acting directly on the center of mass. When we talk about torque, we're going to be talking about how those forces applied off the center of mass are going to cause some rotational effects. And as promised in the work and energy video, we're now getting into that other form of vector multiplication, which is going to be the cross product. So if we first just look at the equation for torque, we have this lowercase Greek letter tau equals force cross r, where r is going to be the distance that the force is being applied from the axis of rotation. So it's not necessarily, the axis of rotation is not always necessarily going to be the same as the center of mass. So if you have, say, like a flagpole pinned, then that pin is going to restrain that pole to only be able to rotate about that point, not the center of mass like it normally would. So if something is free to rotate, then it will rotate about its center of mass. You might have seen some of those demos of like a hammer spinning in slow motion, and it shows you that, I don't have a hammer with me, that the center of mass is going to be really, really close to the heavy end, since the mass is mostly distributed towards one end, and if you watch it rotating, it actually does rotate very, very close to the head of the hammer. And yeah, so let's talk about that cross product. I am not going to go through the exact formulation for the cross product, especially in an algebra-based course and in the mechanics section. We're going to be thinking about what the cross product means in a little bit more of a conceptual way. So similarly to how the dot product could be written as the magnitude of f times the magnitude of d times cosine of theta, the cross product is going to be the magnitude of f times the magnitude of r times sine theta. Again, we want to be really, really careful if we're using this form of the equation that theta has to be the angle between f and r. It's an easy way for professors or whatever gremlins are writing your physics problems to try and trick you by giving you angles that either have absolutely nothing to do with solving for torque, have nothing to do with like being the angle between f and r, or they give you something like the complement where you would have to subtract by 90, or just make sure you're drawing a careful picture to make sure you're using the angle that is the appropriate angle for that formula. The other way that we could think about it, where the dot product was taking the parallel component of f in the direction of d, now we're going to be taking the perpendicular component of f with respect to now the distance they're calling r. And I did bring a prop just to kind of illustrate this concept. So and then we'll get the sign. I guess the other thing before I go into my demo is that the signs are then a little bit different. So they might teach you the right-hand rule. Usually that's not something you get to until you get to E&M. It's supposed to be easy, but I've always really struggled with it actually, of knowing exactly how to use my right hand to give me the right-hand rule. And it is very, very hard to teach over video, so I'm not even going to try because you don't really need it. The only thing that you need to remember is that counterclockwise is positive and clockwise is negative. And as long as you keep that consistent, all of your answers will work out the same. And the next question I usually get from students is, how do I know if it's going to go clockwise or counterclockwise? And that you kind of have to almost play the scenario fully out in your head that the problem is asking for before you can make that decision. So if this is my, I'll hold it here so I'm the canvas. So if this is my kind of little rod, we'll say that it's free to rotate about the center. If I were to hang something on here that then would push down this way, if it were free to move and I push, then it's going to be going clockwise. At least from my point of view, it's going clockwise. So probably from your point of view, it's going counterclockwise. I'll figure out when I'm editing. But this way would be clockwise. If instead I had something pushing up on this end, again, it's going to be blocked by my hand, but that would be in the opposite direction, so that would be the opposite sign. And if we were to switch and instead have something pushing down on this end, this would also be the opposite sign to something be pushing down on this end, because it's causing it to go, again, from my point of view, it's counterclockwise, so it would be positive, but I think it looks like clockwise to the audience. So as far as getting signs and determining whether something is clockwise or counterclockwise, go ahead. I'll put an example of what I draw, but I kind of draw these like two circles that show counterclockwise and clockwise, and then put a positive and negative inside each of them. So I'll put that over here. But otherwise, torque from this perspective is just going to be force times R. And I think maybe what I'll start doing, and I'll continue this in the next couple rotational concept video, is continue to show the rotational analogs to the linear quantities. And then you could kind of hopefully see how you go back and forth between the two. The other thing that we can do is we have a full rotational form of the torque equation, very similar to our F equals ma. So instead of F equals ma, if we swap all those quantities out for rotational quantities, which we now know, we'll have torque equals I times alpha. So again, I is our moment of inertia. That's the rotational analog for mass. And someone's in my front door. And then alpha is rotational acceleration. And when using that torque equals I alpha equation, again, we want to keep in mind that this is basically the rotational form of Newton's law, so that's going to be torque net. I think that's all that I have to say about torque for now. This is kind of leading up again, like I was mentioning, to these static equilibrium problems. So that's kind of like the big juicy part of using torque, but we will go ahead in this video and I'll go through a couple examples of using those two equations that I just mentioned, because we can still solve a lot of things using just those two. So let's jump into those examples. A 2 kilogram mass attached to a 2 meter long uniform rod. Rod mass is 1 kilogram. And the other end of the rod is secured and free to swing back and forth. What is the magnitude of the torque on the pivot point when the pendulum is oriented 30 degrees from the vertical? So I guess first we're just going to start off with drawing our picture. I'll do that on the right hand side over here. So we've got our pivot point, our rod, this is 30 degrees, and our mass at the end. And we'll go ahead and put our forces on here. I guess I'll put a couple labels on here as well. So just the fact that this is going to be our length. So we'll have Fg from the mass at the end. And then we'll also have a contribution from the gravity of the rod itself. That's going to be happening at the center of mass.
which is halfway down the rod, and I'll call that FGCOM for center of mass. The other thing, just for these torque problems and rotational problems, that is good to draw kind of at the get-go is that our counterclockwise is positive and our clockwise is negative. So now we'll go ahead and just highlight some of our given values. So we've got that the mass is 2 kilograms, the rod is 2 meters long, it's uniform, and the rod mass, and then the 30 degrees is already put on the picture. And just because we're always being careful with our theta for these torque problems and that cross product, I'm not going to highlight that and give it a label. But, so we'll just copy this stuff down. So we've got 2 kilograms, center of mass 1 kilogram, and our length is 2 meters, and we're solving for T net. So for our T net, that's just going to be the sum of our torques. And so now we'll go through and just kind of look at whether or not the torque contribution from each of our forces is going to be positive or negative. So for both of these, we're going to have FG is pulling this rod down, and it'll start to pull it to the right as well. So both of these are going to be, you can see the same thing for FG center of mass. This will start to pull it down and to the right. So both of these will be counterclockwise and give us positive torques. So we can write our T net is going to be our torque from the mass at the end plus the torque from the center of mass. I guess the other equation I want to make sure I write out here is just the torque in terms of force. So we can either write that cross product between F and R as the magnitude of the force, magnitude times the distance times sine of the angle between them, or we can write it as the perpendicular component of the force times R. I will go ahead in this example and show both ways, just so you can kind of see how both ways are done, and I'll do the angle first. Torque calculated with sine, and then I'm going to go ahead and just redraw a version of this picture so we can use the geometry to get the correct angle. Let's see, so this would be our length, or just our lever arm, kind of keeping it a little bit general. And then since both of these forces are pointing straight down, I'm just going to draw one force vector and keep it general and just call it F. And then we obviously know that we're going to be plugging in different lengths for that R, but just so that I kind of am following with the formula. And then the angle that we're interested in finding, which I'm actually going to draw on the original picture in a light blue, is going to be this angle, which I'll call phi. And then we have, just going back to this, we have this 30 degrees. And then in order to find this angle between R and F, we're going to have to just break things down into getting some right angles and getting some triangles, and that'll just help us use our geometry to find what that angle is. So if we break up that R vector and just draw some dashed lines and make it into a triangle, we have a right angle on that bottom right corner. And if we follow the rules that for a triangle all the angles have to add to 180, that leaves us with this bottom left angle being 60, and then we have a horizontal and vertical, so that leaves 90 right there. And then this whole angle here is our phi. So then we can go ahead and say, from looking at the picture, that our phi is going to be equal to 60 plus 90, or 150 degrees. So cool. Once we have that, we can plug in and find our net torque. So T net for torque due to the mass at the end, our force is Fg, our distance is the length of the rod, and now we have, I'll just write sine phi because we know we've already found it. For our torque due to the force of gravity from the center of mass, that'll be our Fg COM. That distance that force is located from the pivot point is going to be half the length, so L over 2, and then that is the same sine phi. I'm just going to plug in mg's COM. And now I'll substitute in the variables that we have. We'll go ahead and plug that all into our calculators, and when I plug that in, I get 24.5, and the units on this is newtons times meters. Okay, so now I'm just going to go ahead and solve it the other way, which is going to be torque calculated with the perpendicular. So I'll do that right below, torque calculated with F perpendicular, and I will redraw that picture that we had. With our R and our F. This is still 30 degrees. But now essentially, instead of drawing a triangle with the R, we're going to draw triangles with our F. So our F perpendicular is going to be like this. And then the F parallel component would be here. And if we extend that F parallel line, it just kind of helps see the geometry a bit better, I think. We can see that because of the way that these parallel lines are intersected, so from alternate interior angles, that tells us that this is going to be 30 degrees. And then since further down where the hypotenuse is actually would be intersecting with this line as well, that tells us that this bottom angle between F parallel and F is also going to be 30 degrees. I'll just include that right angle right there. So once we have one angle, we can write the force components in terms of trig functions. So we'll have F perpendicular over F equals sine 30. Now, you may be thinking, 30 degrees is not the same as the 150 degrees that we found above. And you would be correct. However, because these trig functions are repetitive, the sine of 30 will be equal to the sine of 150, and that will be reflected in our answer. So don't fret. I promise we will still get the same answer. But, okay, so let me first rewrite our T-net equation now just in terms of the perpendicular components. So for tau g, we're going to have FG perpendicular times our distance again, which is L, and then we'll have FG center of mass perpendicular L over 2. We'll rewrite those perpendicular components in terms of FG sine 30, FG center of mass sine 30 L over 2, and then we'll plug in our mg's and we'll go ahead and substitute in our values again. And plug that into my calculator, and I get 24.5 newtons times meters. A simple model of a yo-yo is a disc with a string wrapped around the circumference. For this simple yo-yo of mass 1 kilogram and radius 0.03 meters, what is the tension in the string when the yo-yo is traveling downward? What are the angular and translational accelerations? All right, so we got kind of a lot going on here, but start with drawing our picture per usual. Simple model of a yo-yo is a disc with a string wrapped around the circumference. For this simple yo-yo of mass 1 kilogram and radius 0.03 meters, what is the tension in the string when the yo-yo is traveling downward? Should be when the acceleration is downward, but that's okay. And what are the angular and translational accelerations? So we'll draw our picture first. So we've got our yo-yo. We've got force. So we've got the string attached at one end. And we'll put our forces on here. So we'll have force gravity acting from the center. Tension is acting along that string a distance r away. And then because this yo-yo is going to be traveling downward, as the tension is pulling upward, the gravity is heavy enough that this is going to unfurl. So we will have angular acceleration going counterclockwise, and we'll have our translational acceleration going downward. I think that's everything. Oh yeah, our counterclockwise positive, clockwise negative. Otherwise, I think that's everything I need on the picture. We can go ahead and highlight our givens. So we have the mass is 1 kilogram, the radius is 0.3 meters, and then I'm also going to go ahead and highlight the fact that it's a disk, because that is going to tell us that we can use that moment of inertia. So we've got, I'll put a little star next to disk, and then that's going to tell us our I is 1/2 mr squared, and our m is 1 kilogram, and our r is 0.03 meters. Awesome. So then we'll take the sum of the torques, and that's going to be equal to I alpha, and the sum of the forces in the Y will be equal to MA. So the only other equation that I want to throw on here is just going to be that translational acceleration is angular times r. Because there are so many ways to connect rotational and translational, they can kind of ask for a lot of values, even though it seems like you don't have a lot of equations. You have more than you think, it's just a lot of substitution. We'll see that in this problem. So let's go ahead and fill in our forces and our torques. So for torques, Fg is acting at the center, so that will not be providing a torque, but the force tension is acting a distance r from the center, and that is going to be pulling this counterclockwise, so that'll be negative. So we'll have a negative torque from tension equals I alpha. That is already at a 90-degree angle, so we can substitute in for that torque, that'll be the force of tension times R. I'm going to leave that for now. And then for our forces in the Y, we will have Ft minus Fg equals Ma. So now I'm going to go ahead and substitute in the 1/2 mr squared for I in the sum of the torques equation. And also using that A equals alpha times R, we can also write that as alpha equals A over R and substitute that in for alpha. When we do that, we'll end up canceling out the R's. So one of the R's will cancel from the R that's dividing the acceleration, and then one of the R's will cancel from the R that's multiplying the force. And we get negative Ft 1/2 m times A. I'll just move that negative sign to the other side. And that's pretty much all we can do at this point. So now we're going to have to use the expression that we get from setting the sum of the forces equals to MA to get another expression for A in terms of Ft. So all we have to do is just divide out this mass. So we'll get Ft minus Fg all over m equals A, and then we'll substitute this whole quantity in for our A. Ft negative 1/2 m Ft minus Fg over m. So our m's will cancel. And then I will go ahead and distribute that negative 1/2. So Ft is negative 1/2 Ft plus half Fg. Add that 1/2 Ft to both sides to get those tensions together. So we'll have 1 plus a half would give us 1.5 Ft equals a half Fg. We'll divide the 1.5 which would give us 0.33 times Fg, and then we'll do our usual plugging in Mg for FG, and then we could plug in our mass and gravity. So 1 and 9.8, and that gives me 3.26 newtons. Once we have that, we'll go ahead and take that 3.6 newtons and plug back into the expression we ended up from the force equation to find our linear acceleration first. So we'll have 3.2, what did I just say that was? 6 minus mg over m equals a minus 1, 9.8 over 1, and that will give me 6.5, negative 6.5 meters per second squared is the translational acceleration. And then last but not least, we'll go back to, I'll just rewrite it down here and do kind of a little box. So we have linear is angular times r. So negative 6.5 equals alpha 0.03. Oh, divide out that 0.03, and I get 218, negative 218 radians per second squared is alpha.
Okay. And the real life howitzer came upstairs while I was filming. But that's my take on torque. Till next time, happy physicsing. Lucy, bye. You're so angry. I know. You just want to go into bed. You just want to go into bed. Thank you. Oh, thank you. Say bye to the kiddos.